Okay, I don't see any obvious technical reason why the screen is not coming up. Oh, okay, coming up slowly. Okay, good. Sorry for slightly delayed start. Okay, so this is sort of a continuation of our discussion of network flows, except now we are talking about networks that have edge weights or edge costs. So this problem is known as the assignment problem, or sometimes the problem of finding min-cost matching. So the setting now is slightly different. So think about the matching problem we discussed yesterday. So assigning students to tutorials, assigning ads to web pages. And yesterday we treated it as a binary problem. Either an ad can be displayed on a page, or maybe an ad cannot be displayed on a page. In reality, of course, it's not quite so black and white. Right, for each ad, some page may be more suitable than another page. Right, so there may be some, profits to be associated with that, or alternatively cost, and you want to find the best way of matching your ads to web pages. So in principle, you don't want to rule out any way of mapping your ads to web pages, but they're not all equally good. Right, so this is what's captured by the assignment problem. So assignment problem is an instance of a matching problem, if you will, in the sense that we still have a bipartite graph, but now my bipartite graph is complete and weighted. Okay, complete, all edges from left to right are present, and weighted, each edge has an associated cost or weight. So today I'm going to use the terms cost and weight interchangeably. I hope it's not going to confuse anyone. Okay, so left-hand side, right-hand side have the same side, so there's always a perfect matching, but our goal is to find the best perfect matching. And the best I'm going to define as minimum weight. So maximum weight in this setting would be equivalent, so for me it will be, so think of these numbers as costs, so we want to talk about minimum weight. Okay, so here for instance I can match 1 to 3 prime, 2 to 1 prime, 3 to 2 prime. My total cost would be 3 plus 5 plus 4, comes down to 12. Okay, and here by sort of eyeballing this small graph, you can see that there isn't a better matching here. Right, so if you want to beat 12, there are some edges you just cannot use, right, and generally it seems like the best thing to do here. So how do you do it generally? Well, okay, yes, so applications, why do we care? Well, essentially every reason why we cared about bipartite matching yesterday, well, quite possibly this application is better represented by weighted bipartite matching than by unweighted. And of course it goes without saying that if I just want to simulate the classic kind of finding maximum matching problem in this setting, as long as my left-hand side and right-hand side have the same size, I can do it by setting appropriate weights. So for instance, if there is an edge, I set cost to 0. If there is no edge, I set cost to 1. And my goal would be to find a cost 0 perfect matching. Right? So this is a strict generalization. Okay, so how do we think about it? Well, so it's very different from what we did before because it had those weights. Right, so before we also had numbers and edges, but those numbers were capacities, and the weights and capacities have very different semantics. So still, let's try to think about what Ford-Fulkerson does in the bipartite case. Let's try to gain some intuition from the performance of Ford-Fulkerson, and then, kind of building on that intuition, we'll come up with an algorithm for this problem. So it won't be Ford-Fulkerson, but let's for now just think about how Ford-Fulkerson works for matchings. Okay, so suppose we run Ford-Fulkerson on the bipartite matching problems without costs and with unit capacities. So remember I told you capacities can be unit or infinity on the edges of the matching. So let's say unit capacities now. Okay, so what happens then? So let's try to think about the shape of the residual graph. Well, so this residual graph will have some edges leaving S and some edges entering S. Right, so all edges are unit capacitor, so an edge can either go this way or backwards. Right, and we are going to ignore those essentially. So what about edges in this form? Well, if an edge is currently matched, meaning we send a unit of flow on it, then in the residual graph, we have that same edge going backwards. Right, so it was a unit capacity edge, we saturated with the flow, so in the residual graph, it's going backwards. Right, and if it was not used for matching so far, it's still going forward. Right, so it's one of those blue guys. Okay, so now what about these edges? Again, if they are flow-carrying edges, then in the residual graph they go backward. If they're not flow-carrying edges, they go forward. Right, because all edges are unit capacity, all edges in the residual graph go either forward or backward, so we never have anti-parallel edges. Right, just because there's unit capacity and we run classic Ford-Fulkerson, it's integral. Okay. So now flow corresponds to edges in a matching, and residual graph can be simplified in this way. So if there is no, so I'm looking at the projection of the residual graph on x times y, so on this part. Right, so if xy is not in the matching, then xy is in the residual graph. If xy is in the matching, then yx is in the graph, right, so the backward edges. Right, and let's remove edges entering S or leaving T, because those are never useful. Right, so this is a usual convention with all network flow problems. There is no point in keeping edges entering S. They are not useful for anything. There is no point keeping edges leaving S. Right, and now the picture simplifies quite a bit. Okay, so now if you look at it, well now suppose you want to get from S to T in this graph, which is what you typically want to do with the residual graph. Well, now you immediately see how to start. You'd have to go like this, continue like that, and eventually, so here you have a choice, you can go this way, or you can do an extra zigzag and come this way. Right? Okay, so what's interesting here? Well, think about the shape of your path. Well, you start from S, you have to start from S. In this example, there's just one edge leaving S, but in principle, so there could be more. So you start from S, you go to some node that has a forward edge from it. Right? So you go and reach this point. Now, if you're lucky, and from that node there is an edge to T, right, that would be an augmenting path already, like an all blue augmenting path. Right, and this means you just add an edge to a matching. There were two unmatched nodes, you match them, add that edge to the matching. Okay, suppose that doesn't happen. So what can happen then? Well, so you can, if there is no edge going to T here, so that's for a reason. There is no edge going to T because this edge has been used up. This edge has been used up because some flow is already traveling here. So why is there some flow traveling from here to T? Because this node is matched to someone else. Right? And if it's matched to someone else, this means that in your residual graph, there is an edge pointing backward. Right? So this edge. Right? So as you're looking for a path in your residual graph, you can now take this edge going backwards. So if you cannot get to T, you can go back. Right? And as you go back, you follow the edge of the matching. Right? And here, so you may have some path going forward. Right? So in fact, if you started with a complete graph, you will have all these edges going forward. There's just one edge of the matching, all other edges are still available to you. So you can make one step forward again. So you go forward, forward, and then again, either to T or backward. Okay, so what does it tell you about the structure of your path? So the path from S to T has a very peculiar shape, right? So it starts from S, goes to a node in X, then bounces between Y and X until it exits towards T. Right, so think of it as a kind of little ball in a long tunnel, kind of going pop, pop, pop against the walls. Right, so this is what happens here. This is what your path looks like. Okay, so this is what the augmenting path simplifies to: edge from S to an unmatched node, alternating sequence of matched and unmatched edges, and finally an edge from an unmatched node Y to T. Okay, so if I'm doing this on the instance of weighted bipartite matching, so all edges are still present. So if my matching is not a perfect matching, right? If not all nodes are matched, then eventually I'll be able to get from S to T. Right? So simply because there's always a flow of size n, and I don't yet have a flow of size n, so I should be able to augment my flow. Right? So it would be something of this sort. So possibly quite long, but eventually I'll get from S to T. Okay. So this is how Ford-Fulkerson behaves. Okay, so so definition, it will be important for the algorithm. An alternating path with respect to matching is an alternating sequence of matched and unmatched edges starting and ending at unmatched nodes. Okay. So here, for instance, what would be an alternating path? I have to start at an unmatched node. So I have to start at the bottom. And as I start at the bottom, I go zigzag, zigzag, zig, unmatched. Okay. So now suppose that, okay, so here's a little nice piece of mathematical notation. Let me take my matching and let me add this path to the matching. So what do I mean by adding? Well, if an edge of the path kind of is, okay, so this is, okay, add in the sense of symmetric difference. Meaning, okay, so this edge is on the path and not in the matching. I add it to the matching. This edge is on the path and in the matching, so I remove it, it disappears. Right? So this edge is on the path, not in the matching, I add it. Right, so basically, if you think of the matching, if you think of the path as alternating blue, yellow, blue, yellow, blue, yellow, I just swap that. Right, so here I have, so in this path, I have 3 blue edges, 2 yellow edges. Right, so I swap that, I add those 3 to the matching, I remove those 2. Right, so if I do that, I increase the size of my matching by 1. Okay, makes sense? Right, okay. So this is because an alternating path started and ended with a blue edge, right? And it alternated. So I had more blue edges than yellow edges, right? So if instead of using yellow edges, I'm now only using blue edges, right? I have 1 more edge. Why is it a matching? Well, okay. Basically, 3 cases to consider, 2 are very similar. So we have these new edges, right? So we have to argue kind of that they don't ruin the matching property. Well, let's look at this edge. It started at a node that was unmatched. It went here. Right now, this node was matched, but it was matched using this edge, and this edge is no longer present. Right, so this edge is not touching any other edges. It started at a node that was unmatched, and it's touching a node that, as soon as we remove this edge, is unmatched. Right, so this edge is not ruining anything. Right, and similarly for the last edge, it goes to an unmatched node from a node we just unmatched. So what about this middle blue edge? Right, so why is this okay? Well, this point was, this node was matched with this yellow, using this yellow edge, this node was matching using this yellow edge. As we remove both, these nodes don't touch anything in our matching, so I can add this edge. Right, so this is legit. Right, so this set of 3 blue edges, if I add it, I still have a matching, right, and it's a bigger matching. Okay, so far so good. So this shows that if at least, okay, so if I do it this way, I keep building matchings. Okay, this is my new matching, right? I went from size 3 to size 4. Okay, so so now let's think about costs, right? So this was all preparation. So this was just sort of structural analysis of the bifinite matching problem. But fundamentally, we want to minimize costs, right? So perhaps if you want to minimize costs, so it makes sense to think of the cost of those paths, right? And perhaps it makes sense to augment not along just an arbitrary path, but along a minimum cost path. Okay, so what is the right way to think about the cost of an alternating path? Well, as we alternate, so let me take two colors, so they don't match the colors on the slide, but whatever. Okay, so I have green going forward and red that are currently in the matching. Okay, yes?
We were rotating the monitor, so...
I think it's healthier for me to look at the slides as well, not at the monitor. Okay. What is the best I can do? It actually goes out, right, all the way. Okay. Is it fine now? Okay, good. Maybe I should have used the other part of the board, but anyway, so this is what we have for now. Okay, so suppose my matching was red and I replaced it with green. How did my cost change? Well, I added the green costs and I subtracted the red costs. So for the edges, right, so this is the direction of travel of my path. Right, so this is how it goes. So from the perspective of how this segmentation affects the cost of my matching, I should be adding the green costs and subtracting the red costs. Right, so this is how we are going to define the cost of an alternating path. So we paid CXY to match XY, and we receive CXY to unmatch. Okay, so let's see an example. Well, soon enough. Okay, in shortest alternating path, it would be an alternating path from an unmatched node to an unmatched node, like here, with the smallest cost. So we want to augment, and we want to augment as cheaply as possible. Right? And that's essentially the idea. Okay, so here is an example. Okay, so what do we have here? So ignore the type of the line, but so for now we just have one edge in our matching, and it's the edge from 1 to 2 prime. So there are basically two ways for me to augment this matching. Right? So I can add a missing edge. Right? I can simply match 2 to 1 prime. Right? So this is legit. It's like elementary alternating path. Right? Or I can do something more sophisticated. I can go 2, 2 prime, 1, 1 prime, and that would have the effect of replacing this edge with the two parallel edges. Okay. Which one is better, simple or complicated? Complicated, right? So let's look at the costs. So the simple one costs what it costs, so it costs 7. And the complicated one, you pay 2 minus 6 plus 10, so which is 6. Right, so this is cheaper. This is what you want to do. Okay, so the point is, so you're not particularly attached to the edges you currently have in the matching. Right, so if you can kind of have a better matching, right, so you're not sort of cautiously adding things to your matching, you match and unmatch and you look at the costs. Okay. So how do we find, okay, so for now this is a heuristic, right, so I haven't argued that this actually gives a minimum cost matching, but it seems like a reasonable one and we're going to prove that it works. Okay, so let's sort of continue suppose that we actually want to do that. So how do we want to do it? Well, shortest alternating path would be a minimum cost ST path in G of M for properly set costs, right? Okay. So basically I would have to set the cost here at minus 6. All costs from S to nodes and from nodes to D to 0, right? And now I'm looking at the minimum cost path. Okay, minimum cost paths, we know how to do it. You have okay, so we have algorithms for that. Dijkstra might be your first intuition, but we cannot use Dijkstra because we have negative costs. Okay, so this is basically an annoyance. Well, we can show that there are no negative cycles, so at least we can use Bellman-Ford. So that was all pay a shortest path, that works with negative edge weights. So we can sort of efficiently find shortest paths. But Bellman-Ford is slower than Dijkstra. And generally, there are other good reasons for not dealing with negative costs. So we basically want to pursue this idea, the idea of finding shortest path from S to T, but we want to avoid negative costs. Okay, so here's how we are going to do it. We are going to use modified costs. And, okay, so I'll tell you how we modify costs. And there's a nice economic interpretation to it, which I'm not going to cover completely. We may talk about it a little bit couple of weeks later. But, okay, so here's the basic idea. Okay, so here's an observation. So let me take a node here, say node 1, and let me add a constant to the cost of every edge that is incident to 1. Right, so 3, 7, 15, I'm going to add the same constant to each of these numbers. So say, and I'm going to call that the price of node 1. So let's say P of 1 is 3. So I'm going to add 3 to all these numbers. So they become 15 plus 3, 18, 7 plus 3, 10, and 3 plus 3, 6. Okay, so that, okay, what does that do? That uniformly increases the cost of every matching in the graph. Uniformly increases it by 3. Because every matching in the graph has to use one of those, every perfect matching in the graph has to use one of those 3 nodes. So whatever it used to pay, it's now paying that plus 3. So the cost of every perfect matching went up by 3. So in particular, this didn't change the nature of the min cost matching. Right? So whatever was a min cost matching before is a min cost matching for the modified costs. Right? And vice versa. Right? So this preserves the set of min cost matchings. Okay, so think of that as the money you pay to the guy on the left to do the job. Okay, so generally, let's think of our bipartite graph just for fun as tasks for edges, people who can perform these tasks, and people who enjoy the fruit of this task. Right, so people on the left are workers, producers, people on the right are consumers. Right, so this is saying that there is a natural cost associated with each task. Right, and they're going to pay a bonus to guy 1 to do it, bonus of 3. Okay. Okay, so similarly, now let's look at the right-hand side. I'm going now subtract a constant from the cost of every edge incident to node 1. Right, and again I'm going to call that the price of that node. So now I'm saying price of 1 prime is 5, and that means I'm going to subtract 5 from these 3 costs, from 15, from 5, and from 9. Right, so this way I get down to 10, 0, and 4. Right, so these are the modified ones in both ways. And again, by the same argument, it affects the cost of every matching in the same way, so it doesn't change what the optimum matchings are. Right, so I can play with prices on the left and on the right in this fashion. Again, every perfect matching contains exactly one edge incident to y, so it doesn't change the nature of matchings. Now, I can also do that simultaneously. I can do that simultaneously for all nodes on the left and all nodes on the right. Why? Well, think of doing it sequentially. Right? If you added 5 here to all costs, right? So that didn't change the nature of the min cost matching. Then you maybe added 4 here, again, didn't change the nature of the min cost matching. Right? So you can do it for every node successively. Right? So you can have prices on every node on the left and every node on the right. Yeah?
I don't quite understand how it doesn't change the min cost matchings, because by introducing a constant, surely you're making it so that the total path length is dependent on the number of nodes it goes through as well as the total distance it's traveling.
Right, but every path, okay, so every path will use one of those nodes, right? So every path will be affected in the same way. Right, so think of doing it just one node, right? Right, and then by induction we'll argue that we can do it to all nodes. Right, so every path kind of. So let's not say, maybe it's more productive in this context not to think about Force-Falkerson, just to think about perfect matchings. Right, so I'm not talking about how it affects the cost of specific augmentation, so maybe that's the cause of confusion. Right, I'm talking about how it affects the cost of a perfect matching. Right, and a perfect matching does have to match 1 to something, right? So every perfect matching pays this penalty. Right, so every perfect matching is affected in the same way. Okay, good. Okay, so now let's do that for all nodes, and so let's define reduced costs. So I'm going to have a price for each node on the left, price for each node on the right. Nodes on the left will come with a plus sign, nodes on the right will, prices on the left will come with a plus sign, prices on the right will come with a minus sign. Okay, so here by some form of matching, I came up with those prices, right? So my choice. And I'm going to reduce costs using these prices. Right? So for each edge, I'm going to define its reduced cost as its original cost plus price of the left-hand side minus price of the right-hand side. Okay. So what do I get here? Okay, let's pick some arbitrary edge. Right, so how did I get this 4? 4 is 15 plus 0 minus 11. How did I get this 0? 0 is 3 plus 0 minus 3. Right? Okay, so pick your favorite edge, check that it works out. Okay, one more example. So this 6 is 6 plus 6 minus 6, remains 6. Okay, so what is remarkable about this matching here for the reduced costs? Well, it has 0 cost, right? Which is interesting, because every kind of, you don't see any negative numbers here. Right? So all numbers are non-negative. They could have been for a different choice of prices, but for these prices, all numbers are non-negative. Right? So we cannot, so in this modified instance, we cannot expect to have a matching of negative cost. Right? So the best we can hope for, if we're minimizing costs, is 0 cost matching. And I gave you 0 cost matching. Right? Okay, now the actual cost of that matching is of course not 0. The actual cost is 4 plus 5 plus 3, 12. But I know that it's an optimal matching here, because it's a 0 cost matching here, and therefore it's an optimal matching there. Right? So my transformation, my prices preserve optimality. They don't preserve the price of the optimal solution, but they preserve optimality. So what was optimal here is optimal there, and vice versa. Right? Because prices are just a joke. Prices don't affect optimality. Okay, so this is very convenient. Not only do I know, do I have an optimal solution, I also have an easy to check witness to have an optimal solution. Right? So prices actually help me verify that my solution is correct. Right? So now it's easy to check. Right? I don't have to solve the problem from scratch. If I have an instance like that, I can confidently say, well, this is a min-cost matching. Okay, so prices are useful at least for that. Okay. So now, okay, so what characterizes those nice prices? So what was so nice about this case? Let me say that a collection of prices is compatible with a matching if the following holds. All costs are non-negative. Edges on the matching have 0 cost. Right, so like in my instance. Okay. So if I somehow magically manage to come up with this collection of prices, like in the previous slide, then well, if prices are compatible with the perfect matching, right, then M is a min-cost perfect matching. Prices are compatible, meaning this matching has 0 cost, everything else has non-negative cost, so this matching is one of the best. Okay? Okay. So now my goal will be not just to find the matching, but I'm going to look for matching and to also maintain a set of prices. And I'm going to maintain those prices so that they're compatible with my current matching. So my matching, I won't start out with a perfect matching. I will be building my matching slowly, edge by edge. And at each point, I'll maintain prices that are compatible with the matching I have so far. Right? So all costs will be non-negative, and the cost on my matching selected so far, will be 0. Right? So when I get to the end, I'll have a compatible I'll have prices that are compatible with the perfect matching, so I'll have a min-cost perfect matching. Right, so that's my plan. Okay, so how do I go about maintaining these prices? So these prices, well, they can be explained, well, in economic terms, or they can be explained by linear programming duality, which is something we're going to see in a couple of weeks. So maybe I'll talk about the relationship with linear programming duality then, but for now, let's just see what the algorithm does, and let's try to develop an intuition for it. Okay, so this is the description of the algorithm. So we start with an empty matching, so, and 0 prices, and we do the following. So for as long as we don't have a perfect matching, we add an edge to matching and we modify the prices. So how do we do that? Okay. So first we compute the distances. So we care about shortest distances, right? So we still have that concept. So we compute the shortest path distances from S to all nodes with respect to modified costs. Okay. So I have this notation for CP. So let me remind you what that is. So Cp of xy is P of x plus Cxy minus P of y. Right. So these are prices. Okay, so costs modulated by prices. I compute the shortest path distances to everything using the costs modulated by prices. Okay. I'll find the minimum cost ST path, so I can do that actually using Dijkstra if I manage to maintain compatible prices, because compatible among other things means that prices are non-negative. So I find minimum cost ST path, it's an alternating path, and I update my matching, I augment along that alternating path and update my matching. Augmenting means making my matching bigger by 1, right? From unmatched to matched, kind of through some matched nodes and finally to an unmatched node on the right. Right? So remember, so this zigzag pattern, right? So this sort of thing. Minimum cost path from S to T will be of the shape S. So something that looks like this. Right, I'm going to update my matching, right? So now these 3 nodes, 3 edges will be in my matching, right? And then I'm going to update prices, right? So I want my prices to be compatible at each point. So I update my prices according to distances, right? And this is a fairly subtle point. And then eventually I return the matching. Okay, so that's the plan, right? So the algorithm effectively proceeds in n stages. At each stage, it adds 1 edge to the matching, right? And to do that, it computes distances, find the shortest path distance, find the shortest path, flips things along the shortest path, modifies the matching, and then updates the prices. Okay, so that algorithm, I really should have brought in another laptop to keep the description of the algorithm as I do the demo. I don't really want to copy it on the whiteboard. But I hope at least some of you have printouts or something, because it will be useful to look at the algorithm as we do a simulation. So the plan for the next few minutes is to do a simulation. Okay, so that algorithm, so have a good look if you don't have a printout somewhere. Or maybe open your electronic device. Okay, so let's do, okay, so this was basically our instance of matching, but augmented with a source and the sink so that it looks like an instance of network flow. Right, so I start with the original costs, I start with 0 prices. Right, so what do I do first? First I compute distances. So I initialize, now I compute distances. Shortest path distances, okay, so I didn't say it explicitly, but all these lengths, all these weights are 0, all these weights are 0. Right, so the shortest path distances to the nodes on the left are 0, and on the right, well, we're looking at the cheapest way to reach those nodes. So that 1 prime you can reach through 2, paying 5. 2 prime you can reach through 3, paying 4. 3 prime you can reach through 3, paying 1. Right, so those are the distances, and therefore the distance to T is 1. Right, because that's the shortest way. Okay, so my shortest path to T has cost 1. So far, so good. Right, so this is this path. Right, it's not particularly alternating, right? So it's just adding 1 edge, so I add 1 edge. But now something interesting happens. I'm going to add this 1 edge, and now I'm going to update the prices. Okay, so watch the numbers here. So what's going to happen to all the costs? The costs are going to get updated according to these distances. So first the prices are going to get updated, right, and then the costs. Okay, so how do I update the prices? So the prices used to be all 0. Now the price is the way that we update the price is the old price plus distance. So the prices on the left remain unchanged. The prices on the right become 5, 4, and 1. Okay, 5, 4, and 1, fine. So now I compute the reduced costs. Right? So what is now the cost for this edge? Remember it was 15. Now it's 15 plus 0 minus 5, so it becomes this 10. Right? So this was 7. Right? So now it's 7 plus 0 minus 4, so it's 3. So I have to update all costs. Right? So all these prices are non-zero, so I update all costs. So note in particular that this becomes 0. So why does it become 0? Well, it becomes 0 because the distance to here was 1. Right, so the cost of this edge, kind of measured in this direction, would be, it was 1 plus 0 minus 1, so now it's 0. Okay. Good, so that's step 1. So step 2. So now, again, so now I have, let me compute now my distances with respect to those modified costs. Right, so note that, okay, so these two guys are still reachable from S. So the distance to them is still 0. The distance to this guy is 1. How do we get to that 1? Well, to get to him at distance 1, we have to go S2, 3 prime, 3, back to 3. Right, and that costs us just 1. Okay, and here we compute all the distances using our updated modified costs. So for instance, here, for instance, you can get at the cost of 0. Right, and in fact, you can get to t at the cost of 0. Right, if you can go like that, you get to t at the cost of 0, which is what you should be doing at this point. Right? Okay, so this is the path we're going to use. Right, so this is my alternating path. I augment along this path. Right, so I update the prices. Okay, so let's see, what were the prices? Prices were 5, 4, 1. Right, so now the distances didn't, the only distance that changed was that distance. Right, so now my prices, okay, wait. So these are, okay, so these are my current distances. 1 and 1. Right, so and my prices were 4, 1. 4, 1, 1, 1. Right, so they become 5, 2. So I increase the prices according to the distances. So at each step, I increase the prices according to distances. Right, so the prices become this. And note that the edge I have used now has cost 0. Right, so I included it in the matching and it has cost 0, which is how we want it to behave. Okay. So now it will be our final step. We want to go from a matching of size 2 to a matching of size 3. Okay. So what is the, okay. So presumably we want to use this edge. We want to match 2 prime. So we want to match 2 and 2 prime, but we cannot match them directly. Right? So we cannot match them directly because, well, we can get from, we can, okay. So we want to match 1 and 2 prime. 1 and 2 prime. Well, let's compute the distances. Well, the distances are, well, the reduced distances, well, are 6, 1 and 1. So we could potentially match 1 and 2 prime directly. It would be path of cost 1. But we can also do something else. We can do, so we can have a path that goes like this. We can go this way, this way, this way, this way, just to make things interesting. Because that also has cost 1. Right? We could have gone this way, we could have gone this way, and wait. So if we were to match 1 to 2 prime directly, we would have to pay 2. Right, so that was more expensive. Right, so this zigzaggy path is cheaper because it just cost us 1. Right, so the direct path was more expensive, so we went with an indirect path that is cheaper. Right, and this cheaper path has length 1, so we augment along this path. Right, and as we augment along this path and we update the prices, so we get to the point when we have 3 edges and all reduced cost is 0. So we actually managed to maintain compatible prices. Okay, so that was magic. Right, so I suggest that you kind of watch the simulation again, at home, maybe both kind of a printout in front of you and the simulation. But now let's try to prove why it works. So the proof, to me at least, the proof is actually easier to understand than performing the algorithm. So sort of anecdotally, either last year or the year before that, so I gave an instance of matching of size 2 nodes on the left and 2 nodes on the right, kind of as an exam question, right? And even running it kind of for the 2 by 2 instance confused quite a few people who attempted it. Right? So most people attempted, but even 2 by 2 instance you can get confused. 3 by 3, if you can do by hands, okay, so maybe you're better with these things than I am, but yes, there is a huge potential for getting confused. Right, so don't expect to see a 3 by 3 instance in your exam, right? Because, well, I'm not a cruel person generally. Okay, so the simulation may be actually more complicated than the proof. So let's try to do the proof. What do we want to prove? What I want to prove is that my algorithm, well, finds a perfect matching. Well, this part is obvious, so that's not the interesting part. I want to prove that my algorithm maintains compatible prices all along. Right? So that's the interesting part. Right? So I want to prove that it maintains compatible prices, because if I have that, in the end I have a perfect matching and compatible prices, and we have already said that a perfect matching with compatible prices is a min-cost matching. Right? So that's the interesting part. Right? So all our reasoning actually will be about prices. Okay. Okay, so this is termination, perfect matching, compatible prices. So let's prove. This. Let's prove that we can actually maintain compatible prices throughout. Right, and basically this will be 3 lemmas, all of them simple, and they come together to give you a proof. So, okay, so suppose we have compatible prices. And let's look at the shortest path distance in the residual graph with respect to costs modulated by those prices, CP, like here. Right, so then I claim that each edge that lies on some shortest path has cost 0 with respect to prices B plus D. Meaning, if I'm going to recompute my prices as B plus D, which is what the algorithm does, right, the cost of an edge that belongs to a shortest path is going to be 0. Okay. So why do I care to prove something like that? Well, so this in particular will be useful to prove that edges of a matching have 0 cost, right? Which is what we need for compatibility. Whatever is in the matching has 0 cost. Okay, so how do we prove it? Well, let's pick an edge on a shortest path, some shortest path, right? So this edge is useful to reach something. Now, shortest paths have this substructure optimality property, like from dynamic programming. If you use an edge on the shortest path, then this edge in particular, the cheapest way of getting from X to Y, right? So you should actually use that edge if you want to get from X to Y, right? Rather than something roundabout, right? So this is the cheapest way of traveling from X to Y. Okay, so what follows from this? Okay, so suppose XY is in the matching. XY in the matching is like a red edge there. So on the path, we have that edge traveled in the backward direction, right? In the residual graph, it's an edge going backward, right? And it's on the shortest path, right? And because it's on the shortest path, we know that it's sort of the cheapest way to get to X, right? Therefore, the cost of getting to X is the cost of getting to Y plus the cost from getting from Y to X, which is minus CPXY. Right? Exactly because, well, this edge YX is the cheapest way of getting from X, is the cheapest way of getting from Y to X. The cost of getting from Y to X. So therefore, the cost of X is the cost of getting to Y and then traveling that edge. Okay. And symmetrically, even simpler perhaps, if the edge is not actually in the matching, then it's on the path, and we have the similar subpath optimality property. Right, so the cost of getting to Y is the cost of getting to X and then using the XY edge. Okay, wonderful. So in both cases, you can reorder the terms so that you have this nice equality. So dx plus cost CPXY minus dy is 0. Right? Okay, so all we have to do now is to write down what is Cp plus dxy. Cp plus dxy is this. P plus d price of X, this is that, plus true cost, minus P plus D plus price of Y. Okay, so now the thing here in the middle is exactly CPXY. Right, CPXY. Right, so let's substitute. Okay, so now we are left with expression that matches this one, and that one we know is 0. Okay, end of proof. Right, so if an edge is on the shortest path, right, because of sort of subpath optimality property, we can argue that its cost with respect to P plus D is 0. Okay, so things will start coming together in a second. So second, okay, so this is closer to what we care about. Suppose we have compatible prices for M, and let's look at the shortest path distances. Then the prices of the form P plus D are also compatible prices for M. Right, so this means that increasing our prices according to distances, which is what the algorithm does, actually maintains compatibility. Right, that this is something that is kosher to do. Okay, so why is it kosher? Well, let's look. Okay, so what does it mean to prove that these are compatible prices? Well, let's look at the edge in the matching. We want to prove that its cost with respect to C P plus D is 0. Well, okay, it's in the matching. It's in the matching. Right, so now if you because it's in the matching, Yx would be the only edge that enters X in G of M. Right? So generally, think about it. Think about this. So X is in GM. Okay, so let's look at this. Let's look at this X. So what can enter that X? You can enter it from S, or you can enter it going backward. You cannot actually enter it from S because this node is already matched. Right? So this edge cannot possibly be here. So you can only enter it like this. Right? And symmetrically in this way. Right? So if you have an edge in the matching, right? So if you have an edge in the matching, so it can only be entered in this fashion. Right? Okay. So therefore it's on the shortest path. Right? It's on the, so this edge, Yx, is on the shortest path to X, because this is actually the only way to get to X. Right? So we are not two. Right? So the argument we have about edges on shortest path was about edges that lie on any kind of shortest path in our graph. Right? So they don't have to reach, so it doesn't have to be a shortest path to T, it just has to be a shortest path to something. Right? And this is shortest path to X. Right? So therefore this edge is on a shortest path, and therefore we can apply lemma 1. Right? And lemma 1 said that the cost of this edge is 0. Okay, so we proved that all edges in the matching have actually have 0 cost. So what about edges not in the matching? We have to argue that they have non-negative cost. Well, and it's again a very similar argument. Okay, so let's look at xy. It's not in the matching, so it's actually an edge. Xy is currently an edge in the residual graph. And therefore, well, triangle inequality, the distance to y is at most distance to x plus this cost. Right, so we can so the distances we compute according to these costs. Right, so we can always get to y by going to x first and then using that edge. Right, so we have this inequality. Right, and now again we write down Cp plus d of xy. So this is what we want to show to be non-negative. Right, so this is price of x, p plus d price of x, plus cost minus p plus d price of y. Okay? This thing, again, this thing here is Cpxy, this thing in the middle. Right? And now, because of this, we know that this is non-negative. So d of y is at most dx plus Cpxy. So this part is at most that part, we have a non-negative number. Okay? So, and this is exactly the proof that P plus D are compatible prices. Edges in the matching have 0 cost, edges outside of matching have non-negative cost. Okay? Okay? Okay, one more step. So we said that the way we updated prices was legit, but we also update the matching. Right? So the prices were legit with respect to the prices were compatible with the old matching. Right? And our goal is to maintain both prices and matching so that they're compatible with each other. So our prices are we prove that our prices are compatible with the old matching. Are they compatible with the new matching? Right? So this is what we have to prove now. Right? Because we also update the matching. Okay. So this is what this lemma does. So suppose we have compatible prices for matching M, we augment it along our procedure, augment it along a min cost path with respect to C plus D, right? And the new prices are compatible not just for M but for M prime, right? And this means that we manage to execute a stage of our algorithm, obtain new prices and new matching, and the new prices are compatible with the new matching. Okay, so why is that? Well, we know that the prices are compatible with the old matching. We just have to prove it for the new matching now. Well, we augment along our path P, so the only edges whose status changes for being in or out are edges that are on P. Now P is the shortest path, right? So therefore, for all of these edges, actually the modified cost is 0, right? So we don't have to worry about those edges. For edges that come into the matching, the cost is 0. For edges that drop out of the matching, well, we have to prove that the cost is non-negative, but well, proving that it's 0 is good enough. So therefore, compatibility is maintained. Right? So this basically comes for free. Yeah?
Why are we considering M being a min cost path P with respect to CP plus D as opposed to CP? Well, CP plus D was like the overall best path, and we're just trying to get a better step in this exactly.
So P plus, okay, so this is what the algorithm does, right? So we first update the distances and then we compute the paths. Right, so this is how our algorithm augments. It augments along CP plus D at each stage. Right, so this is just matching the execution of the algorithm. Okay, so and that's basically what we need. Right, so invariant that we're trying to argue is that the algorithm maintains a matching and compatible prices. Right, and this follows from lemma 2 and lemma 3. And therefore, so in the end, we have a perfect matching. We have a perfect matching with compatible prices, and therefore it's a min cost perfect matching. Right? Optimality is witnessed by prices. Running time is order of n cube. Right? So therefore this means we have reasonably efficient algorithm for min cost perfect matching. Right? Okay, so n iterations, right, and bottleneck in each iteration is computing shortest path distances, updates achieved. Right, so there you can do Dijkstra order of n squared, so the number of edges we have is n squared. Right. Okay, so you can optimize that further, of course. Pretty much everything we cover in this class can be further optimized, but we're not going to do. So we didn't have time to discuss the economic implications, so maybe if we come back to this in the context of linear programming, I'll tell you a little bit more about this about the intuition. Right, so far this is slightly magic, so I'll also try to have some questions on the sheet that help clarify this magic. Right, and that exam problem from a couple of years ago, kind of 2x2 instance, so that you get the exercise with running the algorithm. So that will be on the sheet as well. Okay, that's it. So see you next week.
No, you take it. Yeah.